the data segment register, so we have got the DS register. So, that is also a 16-bit register, and this data segment register. So, this is used for accessing data, and we have got this for the offset part. So, these registers, this SI and DI registers, so they actually act as the offset part. So, here the calculation will be like 16 into DS plus SI or 16 into DS plus DI. So, that way we can have this 20 bit address computed. So, when I say so this multiplied by 16 means it is left shifted by 4 bits. So, this result becomes 20 bit result, and with that another 16 bit value is added. So, overall value is becoming 20 bit. So, this way we can this 8086 accesses the data part. For stack part, so it uses this stack segment register SS, and otherwise the calculation is same. So, there are two registers which are dedicated for accessing the offset, which is this the stack one is the stack pointer and another is the base pointer. So, both of them the calculation will be that 16 into SS plus SP or 16 into SS plus BP. So, that way it accesses the 20 bit address for the within the stack segment. So, and there is another segment register which is extra segment. So, many times what happens is that we have the one data segment is not sufficient. So, we need to simultaneously access two data segments. So, for that purpose another data segment has been provided by this ES register, extra segment register. So, here also operation can be done, plus this ES-DI pair. So, that also helps in the string operation. So, we will see that 8086 has got a powerful string operation. So, for this string operation, so this is going to be useful. Then this instruction pointer, so that is a 16 bit register, and instruction pointer or IP. So, this is written as IP. So, this points to the next instruction to be executed within the current code segment. So, this IP value is a 16 bit value. So, that will be incremented after each memory access, and that way it will go. So, this 16 into CS plus IP. So, that way the next addresses will be calculated. Next we come to this instruction queue. So, this is a group of first in first out in which we have got up to 6 bytes of instruction code are prefetched from the memory ahead of time. So, as I said that whenever this bus is free, this bus interface unit, so it will fetch the successive bytes from memory. So, we have got instructions in 8086 which varies from 1 byte to 6 bytes. So, that way this 6 byte instruction queue has been provided, so that those instructions can be prefetched. So, this is done in order to speed up the execution of overlapping instruction fetch with execution. So, as I was telling, overlapped fetch execution, and this mechanism is also known as pipelining. So, this execution fetch and execution they are pipelined. Next we will look into the execution unit part. So, this execution unit it decodes and executes the instruction. So, that is the major responsibility. A decoder in the execution unit control the execution unit control system translates instructions. So, this is this control system. So, this is translating the instructions into the control signals to see how these instructions can be executed. There is a 16 bit ALU which performs the arithmetic and logic operations. 4 general purpose registers AX, BX, CX, DX. There are 2 pointer registers, stack pointer and base pointer, and there are 2 index registers SI and DI. Okay. So, these are the several registers that we have in the execution unit. Some of the 16 bit registers can be used as 2 8 bit registers, like this AX can be taken as AH and AL, 2 8 bit registers, BX can be taken as BH and BL. So, like that. So, this AX is the accumulator. So, just like 8085 we had A, so here we have got the AX register. It consists of 2 8 bit registers AL and AH which can be combined together and used as a 16 bit register AX. AL in this case contains low order byte of the word and AH contains the higher order byte. The IO instructions that use AH or AL for inputting or outputting 16 or 8 bit data to from an IO port. So, this is for IO access, and multiplication division instructions also use AX or AL. So, we have got multiplication division operation that use either AX or AL. Then there is another, the next register BX. So, this is called base register. So, otherwise this is a general purpose register. So, you can use it for other operations like so holding some data operand, performing addition subtraction operations. So, for that you can hold it at some of one of the operands there. So, again BL is the lower order byte, BH is the higher order byte. So, this is the only general purpose register that can be used for addressing the 8086 memory. So, that is why it is called the base register. So, particularly when you are accessing say array type of location. So, this BX register can be used as to hold the base address. So, we will see that later. All memory references utilizing this register content for addressing use DS as the segment register. So, DS is the segment register and BX will be the offset. So, like that it will be done. Then there is another register CX. This is also general purpose register, which is given the special name counter register. So, the name comes from the fact that for some instructions like shift, rotate, loop, etc. So, we have to tell like by how many bits we want to shift or rotate, or for a loop instruction. So, 8086 allows you to repeat a block of statements a number of times. So, how many times that block will be repeated, that is determined by the CX register content. So, this will be that is why the name counter comes here. So, this CX is called the counter register. The instruction loop start. So, this automatically decrements CX by 1 without affecting flags, and we will check if CX equal to 0. So, loop start whenever this instruction comes. So, the control start is actually a label. So, it will be going back to that start point and it will again start the execution of the loop. So, normally what we do is that if we want to make a loop, so we keep this body, and so this is the label start, and at this point we say loop start, and before that somehow the CX register is initialized to number of times we want to repeat the loop. Suppose we want to repeat it 10 times. So, it will be when it comes here. So, CX value will be decremented. If it is non-zero, so control will automatically branch to this. So, we do not have to spend any more instruction for that. So, if it is 0, so it will be 8086 will execute the next instruction, otherwise it will branch to the label start. Okay. Then there is a data register DX. So, this is for holding data. So, this does not have other special functions. So, it is DL, it can be divided into DL and DH. It is used to hold the high 16 bit result in 16 into 16 by 16 multiplication, or the high 16 bit dividend before a 32 by 16 division, and the 16 bit remainder after division. So, this is particularly used for this data operation, that is why the name data register has come. Other two registers are stack pointer and base pointer. So, the stack pointer is they are used to access both SP and BP, they are used to access the stack segment. SP is used as an offset from the current stack segment during execution of instructions that involve stack segment in the external memory. So, basically the local variables, the parameters that you pass. So, for the accessing those, this stack pointer is used. And then this stack pointer, this SP BP content, so they will automatically be updated, incremented or decremented for a pop or push type of operations. And BP is a special register. Sometimes using stack pointer alone is not sufficient, because stack pointer may get corrupted. So, if we want to access within the stack segment, then this BP pointer may be used. So, what I say is like this, that is if this is the memory and maybe so this part is the stack. Okay, so, this whole thing is the stack. So, your stack segment register points to this, and now to access individual locations within this. So, one option is you can use the stack pointer to do that, but the stack pointer if it gets corrupted, then this return address will be a problem. Okay, return address may get may be modified. So, what we do, instead of that stack pointer, the base pointer register is used to get offsets within this, and stack pointer is not touched, so that this procedure call return can work properly, but for accessing parameters and all we can use this base pointer. So, both of them will use stack segment as the base register. So, another pair of registers which are common in 8086 is the source index SI and destination index DI. So, they are used for indexed addressing. and also for the string processing. So, this SI and DI purposes, so we will see later when we go for this string operations. Flag register. So, there are a number of flag bits like this carry bit. So, carry flag is there, this is carry, then we have got parity, then there is auxiliary carry, then there is 0, then we have got the sign flag, then this trap flag. So, this is it can generate some internal interrupts. So, this is mostly used for debugging type of operation. Then there is the interrupt flag. So, it will cause the 8086 to recognize external mask interrupts. If you clear this IF, then it will disable all the interrupts. So, that is the same thing that we have with say rim sim type of instructions in 8085. Then there is a DF flag which is direction. So, direction flag it will be clear when you go to the string instructions, and there is an overflow. So, if an overflow occurs, then this flag will be set. So, these are various flag registers that we have in 8086. Now, this overall registers, so they can be classified into a number of groups like general purpose registers. We have got 16 bit or 8 bit, 16 bit AX, BX, CX, DX, 8 bit AL, BL, etc. We have got pointer registers SP and BP, we have got index registers SI, DI, instruction pointer IP, segment registers, we have got the CS, DS, ES, SS as 16 segment registers, and there is a flag which is flag register, which is again 16 bit. So, this summarizes the operations. So, we have already discussed about them. Next, we come to the addressing mode. So, there are different addressing modes which are possible in 8086. Like the first addressing mode is the register addressing mode. So, the instruction will specify the name of the register which will hold the data to be operated by the instruction, like move CL comma DH. So, the values are available in the registers only, CL will get the content of DH. So, this is the content of 8 bit register DH is moved to another 8 bit register CL. Then there is immediate addressing when where the source is an immediate one, immediate value, like move DL comma 08 hex. So, this 08 hex this immediate value is moved to the DL register. In 8085 we had MVI type of instruction. So, here we do not have MVI. So, here it is move only. So, operand itself will identify that this is an immediate operand. Then move AX comma 0A9F hex. So, this will be this is telling that we want to move this number to the 16 bit number to AX register, out of which this AH will get 0A and AL will get 9F. Then for memory access, there are 20 address lines. So, 8086 can address up to 2 power 20 or 1 megabytes of memory. However, the largest register is only 16 bit. So, physical address that is formed, so that is calculated as the actual address of a byte in the memory, that is the value which will go to the address bus. So, this is in the form segment colon offset. So, this is the segment and this is the offset part. So, how is it? So, that means it will be starting, the segment register will contain the value 89 AB and the offset register will contain the F012, and the calculation will be done like this, that this segment register value will be left shifted by 4 bits. So, in hexadecimal notation it becomes 89 AB0, and with that this F012 will be added. So, this is the absolute address that is put onto the bus. So, as I was telling, the value calculated is 16 into segment register plus offset, 16 into segment plus offset. So, that calculation is being done here. So, next we will be looking into direct addressing. So, in direct addressing the address is mentioned directly. So, this move BX comma 1354 hex. So, this 1354 denotes the contents of the location to be accessed. So, this is when executed, the instruction will copy the content of the memory location into BX register, and the actual operation the memory content the BX will get the content of memory location 16 into DS plus 1354 hex. So, content of this particular memory location will come to the BX register. Similarly, this BL 0400, so 16 into DS plus 0400, so that will come. So, we can this addressing mode is called direct, because the displacement part of the operand from the segment base is specified directly in the instruction. So, it is given here directly. Then register indirect addressing mode. So, here with the offset part is contained in some register, like say move Cx comma within bracket Bx. So, Bx content will be used as the offset. So, this effective address is the content of the Bx register, and this memory will be this base address, that is DS register multiplied by 16 plus this effective address. So, this way we will be calculating the total actual address value. So, in this instruction, so Cx will get the content of memory location MA, which is computed, the address is computed here, memory address, or it is equivalent to this. So, CL getting MA and CH getting MA plus 1. Then there is a based addressing mode. So, where this base register Bx can be used to give the offset part. So, this Bx will hold this effective address, which is this 20 bit physical, and 20 bit physical address will be calculated from Bx and Ds, like here. So, Bx with this Bx, this 08 hex will be added. Okay. So, this Bx plus 0008 hex is added, that gives the effective address, and base address is Ds into 16, and the actual memory address is MA plus BA plus EA. So, that is giving the memory address. So, then this AX register gets the content of memory MA, or it is equivalent to this. So, this way this base register BX is used for based addressing. Then we have got indexed addressing. So, in this indexed addressing, this index register SI or DI, they can be used to hold the index value of the memory location. So, this move Cx comma SI plus 0A2 hex. So, this will be containing this EA, the effective address will be SI plus this offset. So, this 0A2 hex, so when it is sign extended, so it will become FFA2 hex. So, that will get added, and this will be multiplied, base address will be multiplied by 16, DS multiplied by 16 will give the base address, and memory address is calculated like this. So, this is, it is sign extended to 16 bit before adding to the base value in case of indexed addressing. Then we have got this based indexed addressing, where the base register and this index register. So, both are used, like move dx comma bx plus si plus 0a hex. So, this is sign extended. First of all, this 0a hex is sign extended. So, it remains, it becomes 000a, and effective address is bx plus si plus 000a, and this base address is ds into 16, and actual memory address is ba plus ea. So, then the content of this memory address is transferred to the dx register. So, that is the base addressing. Then there is one string addressing. So, this is employed in string operations to operate on string data. So, we have got in 8086 instructions called like moves type of instruction. So, here we have got one example, moves byte. So, here the operation that is done, the effect that so when I say moves, that means we are trying to move a byte from one memory location to another memory location without involving the without involving a transfer to a processor register. So, how is it done? So, this effective address for the source memory location. So, this effective address is available in the source index register SI, and DS contains the base of that. Actually, the idea is like this. So, if this is your memory, and then if this is, so this may be the source block S, and this is the destination block D, and we may be interested to transfer the content of this memory location from here to say here. We want to transfer it to here. Now, how to do that? So, DS register points to this, ES register points to this address, and then this SI contains this offset. So, SI is SI contains this difference, and DI contains this difference. Okay. So, when this moves instruction is executed, first the content of this memory location is taken. So, 16 into DS plus SI. So, that gives the memory address, source memory address, and for the destination address. So, this is 16 into ES plus DI. So, that is done. So, that becomes the destination address. Then this location's content is transferred to this location. And then depending upon the direction flag setting, so df is made equal to if df is equal to 1, then this si and di are decremented by 1. If df equal to 0, they are incremented by 1, si and di are incremented by 1. So, this is the string addressing. So, we will be looking into instructions later, but these instructions are useful, like when you are trying to transfer a chunk of memory block from some memory locations to some other memory locations. So, this can be used. For IO port addressing, so there are 3 addressing, these addressing modes can access the standard IO mapped devices or ports. So, you can have in AL, 09 hex. So, this is a 8-bit port address. So, this is a direct port addressing. So, you can mention one 8-bit port address, like here 09 is the port address. So, this AL gets the content of the port whose address is 09 hex. And in indirect port addressing mode, so this port address is a 16-bit address, and that 16-bit address should be available in some register. So, for example, it may be 16-bit port address, so it is stored in the dx register. In that case, so we can say like out dx comma ax. So, that means then the content of this ax register will be outputted to the port whose address is available in the dx register. So, this way we can go for this IO port addressing. Then there is a relative addressing. So, in this addressing mode, the effective address of a program instruction is specified relative to the instruction pointer by an 8-bit sign displacement. So, what is done? Suppose, so this is in relative addressing is in relation to the jumping within the program. Like if we want to jump from, say, suppose we have written a program where we have got these statements, and at this point from this point I want to jump to this address. Okay. So, then the one possibility, if this address is say 10,000. So, I can directly say here jump 10,000. But the problem with this type of concept is that if it is next time the program is loaded from a different address, then this 10,000 address may not be valid. Maybe this should actually be say 50,000. If the program is loaded from a different address, maybe this address should be 50,000. So, just to avoid that situation, so in case of relative jump, what we do? We tell the distance between these 2 points. Like here, so we say jz jump on 0. If the 0 flag is set, then it will jump to 0a hex. But what is actually done is, with the current instruction pointer value, this 0a hex will be added. And when this addition is done, then so we have got this new address calculated, and then wherever the program is loaded, this distance between these 2 points always remain like 0a hex. Okay. So, that way this distance is unchanged. So, we do not have any problem there. So, it is irrespective, it is not dependent on the address at which the program is loaded. So, in case of 8086, we have got this relative addressing, and this relative addressing will help us in making the program relocatable. Then there are implied addressing, where we do not need to tell the operand, like this CLC. So, clear carry. So, clear carry means the carry flag will be cleared. So, there no other operand need to be specified, because it is directly specified in the carry flag. Next, we will be looking into the instruction set. There are 6 types of instructions supported in 8086: data transfer instruction, arithmetic instruction, logical instruction, string manipulation, process control, and control transfer. So, data transfer instructions. So, the instructions that are used to transfer data or address into registers, memory locations, and IO ports. So, they come under this data transfer instructions. So, we have so whenever we have got data transfer, we need to tell the source and the destination. So, the source operand and destination operand, so they are of same size. So, source may be register or memory location or an immediate data. Destination has to be a register or a memory location. So, naturally immediate cannot be the destination. So, we have to have some memory location or a register, and we cannot have both the operands as memory. So, it is not possible that both the operands of this data transfer instruction they are memory, excepting that string type of operation. So, it is not possible. So, size should be either a byte or a word, okay. And the 8-bit data can be moved only to 8-bit register or memory, and 16-bit data can be moved to only 16-bit register or memory. So, here we have got a few example, like these are the common mnemonics that we have with the data transfer instructions: move, exchange, push, pop, in, out, etc. Like we can have say move register 2 comma register 1. So, register to move AX comma BX, like that. Move memory comma register 1. So, we can specify some memory address and the register 1 content is moved there, or this is from this memory location the value is loaded onto this register. Then we have got this register, this is for the immediate part. So, we have got some immediate data may be mentioned and that goes to register or that goes to memory location. Then we have got exchange. So, exchange means these two contents are exchanged. So, register 2 register 1 are exchanged, or this memory and register 1 are exchanged. So, these are the move instructions. Then the push instruction. So, we can have this push register 16-bit register or push memory location. So, if it is push 16-bit register, first the stack pointer is decremented, address is calculated. So, this is 16 into SS plus SP, and then the two locations, this location and the next location. So, they get the content of this 16-bit register. Similarly, push memory. So, here also similar thing, the content of this memory location and this next location, total 16-bit location. So, that they move to stack. Similarly, the reverse of push, we have got pop instruction. So, that can also work in conjunction with 16-bit register or memory. Then this IO operation like in instruction. So, in AL comma DX. So, this is the DX register contains the 16-bit port address and that value comes to AL register. So, or you can move a 16-bit data can be moved. So, by means of this AX. Okay. So, you can say like in AX comma within bracket DX. So, that way the port 16-bit port value comes to the AX register. Or we can similarly we have got this, if you are doing immediate addressing, then this is the 8-bit address we can mention. Okay. So, this we have already seen. Similarly, for the out instruction also we have got either 16-bit port or 8-bit port. Then under the arithmetic instruction category, so we have got all these instruction: add with carry, subtract with borrow, increment, decrement, multiply, division, compare, etc. So, add is register 2 register 1. So, this is register 2 will get register 1 plus register 2, add register 2 memory. So, register 2 gets register 2 plus memory. So, like that we can have a number of different types of add operations. Note one thing, that there is nothing like add memory 1 comma memory 2. So, both the operands cannot be memory, one of them must be a register. Then this add register memory comma data. So, here this is the immediate addition, that is ADI is a type of instruction that we had in 8085. So, this is this data value will be added to the register, or here this data value will be added to the memory location. Then add A comma data. So, this is again the 8-bit addition. So, this way we can say AL AX. So, AL sorry this is this A comma data. So, this 8-bit data can be added to AL, or 16-bit data can be added to AX. Then this ADC, add with carry. So, we have got a different types of add with carry instructions here. So, we can do that. So, otherwise it is same as the add instruction.